chapter 14, and we got into last time the common ion effect. And the idea of the common ion effect is really, as we'll talk about today, the idea of buffers. And the idea here is you have something like a weak acid or even a weak base that will set up, obviously, its equilibrium. And if you have just, for example, here, acetic acid or the weak acid in your beaker, it will obviously dissociate here. It will produce a certain amount of H plus. Obviously, it's a weak acid, so it's not going to produce as much as a strong acid would. But if you took that same weak acid and you added something like a salt to it, like sodium acetate, because sodium acetate is a salt, it's a strong electrolyte, which means it will 100% break apart into its ions when it's in solution. So you basically would have both of these ions flying around. And floating around in there would then be acetate, which means essentially you would be adding more acetate to this equilibrium. And Le Chatelier's principle tells us when it adds, we shift away. So we would expect the equilibrium to shift away in the presence of this common ion. What that's going to do is keep our weak acid together. And ultimately, what that's going to affect, obviously, here is our concentration of our H plus. Because it's going to shift it to the left, we will actually see a decrease in the amount of H plus. And the result of that is we'll actually see a sort of higher pH. We expect a higher pH than we would if we had just a weak acid by itself. So we would expect that effect of the common ion. It would also do the similar sort of effect on a weak base. If you had a common ion with a weak base, it's going to keep that weak base together. And what that's going to mean if you had a weak base type of situation, you would then be basically shifting away from the hydroxide. It's going to keep it together. So it's not going to produce as much hydroxide, which means in this particular case, you would have a lower concentration of hydroxide. The result of that is actually you'd have a higher concentration of H plus. And in this case, we would expect actually the pH to be a little bit lower than it would be in a weak base by itself. So it can work in both of these sort of situations. To handle these sort of calculations that are common ions or really buffer type situations, we could do one of two things. We could still do an ice table. And the importance of the ice table is really the initial sort of part of it. You need to have an actual number over here on this side. And if you do 0, then you're obviously not doing the common ion sort of calculation. So that's a really common mistake that people make is they kind of zero out the right-hand side in this situation. But you do need an initial of your common ion on the right. The opposite way is if it is a common ion or a buffer, you could use the Henderson-Hasselbalch equation, which is the pH is equal to the pKa plus the log of the concentration of the base over the acid, where the pKa value is negative log of the Ka value. So this is an equation that you can, if you recognize it as being a common ion or really a buffer situation, you could go right into that equation. If you don't want to or not sure, you can, again, always still do the ice table. They both will give you the same answer. I think we did one both ways there. Last time we did the ice table first, and then we put it basically into the Henderson-Hasselbalch, and we got basically the same pH. Any questions on any of that there? All right, so I'll try one here. I think it's where we left off. What is the pH of a solution that contains 0.3 molar formic acid and 0.52 molar potassium formate in this case? Okay, let's take a look. And again, a couple things you might want to look at is obviously we have this guy and this one, and they are related to each other. Hopefully you could recognize this. This here would be our acid, and this would be our conjugate base here, or our salt in this case. This is basically HCOO minus and K plus. So again, the relationship is between these two things. are the guys that are related to each other by 1H plus in this case. If you recognize that right off the bat, you can go right into your Henderson-Hasselbalch equation, pKa plus the log of the base over the acid. Once again here, to get the pKa, that is minus the log of the Ka value, negative log of 1.7 times 10 to the minus 4. And that's going to get us here 377, we'll call it. That gives us the pH is equal to 3.77 plus the log. Once again, this here would be our base, as this is our acid. Again, it has one more hydrogen than the other one, so that tells you it is the acid if you weren't sure. Also, this guy's got like a spectator ion, like a potassium, a sodium, or something in it as well. So we're going to go our base, which is 0.52 divided by our acid, 0.3. And we'll go 0.52 divided by 0.3 log of the answer and add it to 3.77. That's going to give us a pH here of 4.01 in this case. Now, if you chose not to use the Henderson-Hasselbalch, you could have used the ice table. Once again, it's going to be the weak acid that's going to set up the equilibrium. So if you took more of the ice table approach, you would have something like this, just a basic weak acid breaking apart into its ions. Initially here, this would be 0.3, 0, and the important part here, we do need an initial number here, and this should not be 0. Change would be minus x plus x plus x, and that would get you 0.3 minus x, x, and 0.52 plus x. This would go into your Ka, which obviously would get you x 0.52 plus x divided by 0.30 minus x, and that would equal 1.7 times 10 to the minus 4. You would assume x is equal to 0. You would solve for x and eventually get in there, and you'll eventually get to the same answer. If you kind of go through there, the assumption would be good in this case, and it should lead you to the same answer. Any questions on either way there? So once again, as we talked about a couple of things with the Henderson-Hasselbalch equation, just a reminder, you should not use it in every situation. It should really only be used in a common ion or really a buffer situation. For most cases, if you do use the Henderson-Hasselbalch equation here, molarity is a good thing to put in there, but it will actually work with moles on top and bottom if you want to do that. So if you're using Henderson-Hasselbalch, you could use moles over moles, the moles of the base over moles of acid. It will come out the same. And that's because the volume will basically cancel because you're dividing. Any questions on that there? All right, so really what we've been talking about here are buffers. And common ion is pretty much what happens in a buffer situation. And let's talk a little bit about a buffer and sort of what it is, how it works, and all that good stuff. A buffer is a solution that's basically made up of pretty much one of two combinations. You could either be a weak acid and the salt of its conjugate base, or a buffer can be a weak base and the salt of its conjugate acid. What is the difference between these two? It is, again, the basic Bronsted-Lowry definition. In order for something to function as a buffer, the only difference between those two things has to be 1H plus, rest for them to be obviously pairs. So it's the same sort of definition in this case. They both actually need to be in the solution to begin with in order for it to be a buffer. So you can't just have one and not the other. You got to have actually both of those things. So a buffer actually has like an acid part to it and it has a base part to it. And they both actually need to be swimming around in the solution to begin with. One of the things that people have a misconception about in terms of what buffers are is They think a buffer needs to be neutral, and a buffer is not a neutral solution. It can be neutral, but it could also be acidic. It could also be basic. It could actually make a buffer at any pH you want. But what a buffer is able to do is resist changes in pH, even when you add additional acid or base to it. So that is what a buffer is. So for example, if you made a buffer at a pH of 4 and you decide to add some acid to it, it will probably go down just a little bit, but it won't go down tremendously if it's a good buffer. And it will still be around a pH of 4. Maybe it drops to 3.9 or something like that. But it will not go from like a pH of 4 all the way down to like a pH of 1. So you won't get this really big drop in pH when you add your acid. Same thing if you made a buffer at a pH of 4 and you added some base to it. It would go up a little bit, but you won't see a big jump in the pH by adding base. So it won't go from like a pH of 4 to like a pH of 10 or anything like that. Maybe it goes from like 4 to 4.1, 4.06, something like that. So it goes up just a little bit. So that is what a buffer is. It is a solution that's able to resist changes in pH. When you decide you want to add either some more acid or base to it, it'll be able to really maintain that pH. It has to be made out of a weak acid or a weak base. You cannot have a buffer out of anything that is strong. So anything that's a strong acid or strong base cannot be a buffer because, for example, when you put in your solution, you need that equilibrium set up between the acid, basically, and its base. So you got basically the acid part of the buffer, and you got the base part of the buffer. And again, they both need to be in that solution together. The reason you cannot make it out of a strong acid or a strong base is very simple. Let's just say you wanted to make a buffer out of HCl and sodium chloride. You may say to yourself, well, they are related to each other. That's obviously HCl and Cl minus. So if you were going to make this as your buffer, what would happen, because the hydrochloric acid is a strong acid, is it is going to 100% break apart into H plus and Cl minus. And obviously you'll have some Cl minus and sodium from your sodium chloride, which means in your beaker, you essentially will only have these things, which means you only have really the base part of a buffer, which is not really a buffer, and you don't have any acid part. So this cannot be a buffer. So you cannot have a buffer of anything that is strong because it won't be able to set up an equilibrium and keep both the acid part and the base part of the solution together in the solution at the same time. Only weak acids or weak bases can do that because they are weak electrolytes and they're able to keep both of those things in solution at the same time. You help it along by adding a little bit more of the conjugate salt basically in there. Any questions on that there? So a buffer will be able to resist that because it does have that acid and base component, and it's really important for how a buffer is able to function. So let's take a look at that and talk about how it's able to function. Let's start with something that is not a buffer, and something that is not a buffer like water. And if I take a strong acid and I add it to water, which is not a buffer, if I take some hydrochloric acid and I add it to water, I am going to get, as I just mentioned, it to completely break apart into its ions. You will 100% have these ions floating around. So what happens is if you look at your beaker there and you take your HCl and you dump it in, you just generated a lot of H plus very quickly and some Cl minuses basically. But in terms of the pH, you have now a lot of free H pluses. And what that's going to mean is the concentration of H plus can go up a lot, and you're going to see the pH drop a lot. So as the H plus concentration increases, pH goes down. So in this case, maybe your water started at 7 if you're lucky, and the pH goes down to like a pH of 1, right? You're going to see this really big drop in pH because by adding that HCl, basically all that free H plus is now in the solution. And that again is what affects pH, right? Is the concentration of H plus, as we know, right? So that is not going to be a buffer, obviously, in this case. If you added sodium hydroxide to water, Same thing. Sodium hydroxide is a strong base, which means it's going to 100% break apart into sodium ion and hydroxide ion. Again, none of these guys on this side. So if you look at your beaker in this situation, when you take that sodium hydroxide, you're going to drop it in there. You're going to create a bunch of sodium ions, which is not all that bad for the pH, as we know it's neutral. But really bad for the pH is the other thing that would be created, which is a bunch of free hydroxide. So by adding that strong base to water, which is not a buffer, you're going to see the amount of hydroxide increase. So the concentration of hydroxide will go up. And remember that H plus is tied to that. So by contrast there, the H plus concentration will actually go down. And the result of that is your pH will go up. So here you would expect to see a really big jump in the pH because you just influxed into that solution basically a bunch of OH minuses freely floating, and that's going to cause a very big shift in the pH of that solution. Any questions on that? So this is what happens when we add acid or base to something that is not a buffer. We get a lot of H plus formed or a lot of OH minus, causing the pH to really jump. So what happens when we add like those same guys to a buffer? So I'm going to use this as my buffer because I don't feel like writing acetic acid all the day. So we'll do something different. So we're going to go we're going to go hydrofluoric acid and a little sodium fluoride. This is a buffer. I know this is a weak acid. It is definitely not one of my 6 strong acids. This is his conjugate base, or the salt of his conjugate base. This sodium fluoride is a sodium ion and a fluoride ion. And the buffer part of this are these two guys. These are really the buffer part of it here. And that is, again, the basic Bronsted-Lowry definition of 1H plus difference, right, between the HF and the F minus. Again, the sodium is neutral, just hanging out to balance out the charge, not really doing much. So when we have this buffer solution to start with and we put it in there, it actually will set up its equilibrium. Throw the arrows in there for good measure, right? That's a little F minus. So we'll have basically these things floating around. And in this buffer solution, we basically have, as I mentioned, 2 parts to it. We have this part of the buffer, which is the acid part. And we have this part of the buffer, which is the base part. And again, they are both in the solution to begin with. And that is really vital to how a buffer is able to function. So what happens if we do take hydrochloric acid and add it to my buffer here? So if I take my HCl and I add it to my buffer, the HCl is going to react with the HF or the NaF. Which one will it react with? HCl is a acid, and the reactions are called acid base reactions. So when you dump that into here, it's going to react with the base part of the buffer in this case. It's going to do a double displacement reaction, dare I say it, there it is. We're going to switch partners here. And we're going to get, in this case, a little HF. And we will get a little sodium chloride at this point. So what we do get when we add this into our buffer, which is basically H plus and Cl minus, we get the formation here of HF, which was part of the buffer to begin with. So that is definitely not going to screw up the pH because it was there to start with. And by the way, that always happens if you add acid or base to your buffer. It will actually use part of your buffer, but then make the other part. So the other part is always made while you use the one part gets used, one part gets made. The other thing that we made here is sodium chloride, which is a salt, and hopefully you remember it is a neutral salt, right? As it comes from like sodium hydroxide and hydrochloric acid, and it's not going to affect the pH. So we made something that is part of the buffer, and we made a neutral salt, and here we're not going to affect the pH either of those. But it is actually what we don't see here that we did see when we added to water that's really important. What do we not see in that reaction that we did see over here when I added it to water? And when I added to water, what did I produce? A lot of H plus, yeah. So I produced a lot of H plus when I added the HCl. And when you look at when you added it to the buffer, we did not produce any free H plus, right? And what that will essentially do is, because we didn't create any more H plus, the concentration of H plus will stay relatively constant. And because the concentration of H plus stays relatively constant, your pH will also stay relatively constant. Now, will it move? It will, and that's why I say relatively, but it should move just a little bit. You shouldn't see a giant jump in the pH or drop in the pH in this case when you add that. And that is because when you add the HCl in here, what happens is this guy right here that's being added goes and finds this guy, and then they make that guy right there. And again, it does not allow the free H plus to enter the solution and kind of remain in the solution by itself. And that is the big factor that affects pH, is how much H plus is freely in the solution that you have. Questions on that there? What happens when we add our base to the same buffer? So let's say we took our sodium hydroxide and we want to add that to our buffer here. So once again, we have our kind of buffer over here. It's got our equilibrium made up here of our acid part, our base part of the buffer. And now we're going to add some sodium hydroxide, which is really sodium ions and hydroxide as sort of the source of those things. Obviously here, sodium hydroxide is a base, which means when I add it to my buffer, it should react with the acid part of the buffer. And here we're just going to get a basic acid-base reaction. And in this acid-base reaction, we will make a salt and water. So we will make H2O. Also, by the way, a double displacement reaction. These guys are just going to switch partners, basically. And we will make sodium fluoride in this case. Once again, here we made water, which is neutral, so that should not affect the pH. We made, as we saw in the previous one, the other part of the buffer. So again, we kind of use part of the buffer up and then make the other part of the buffer. And again, is really what we do not see here that we saw with our base and water addition. And that is when we added our base to water, we made a bunch of free OH minuses. And when we look at our buffer, no free OH minuses were made. And because that means that the OH minus concentration stays relatively constant, and because OH minus and H plus are tied together, as one goes up, the other goes down, if the OH minus stays constant, then the H plus will stay relatively constant. And once again, we will have a relatively constant pH value because of that. So once again, it will go up a little bit, but it will not be a big giant jump upwards in your pH if your buffer is made correctly and everything is good in terms of what you added. Any questions on that there? Yeah. No, it's just a separate reaction. Yeah. I mean, it could be, but it's just a separate reaction, really. Yeah. So it's if you added the acid in the first one to your buffer, and or you then you added like a base to the same type of buffer. Yeah. Because the buffer has both of those things in there to start with. The HF and the NAF are in there to start with. So they're both available to react. Yeah. And in the case of the top one, we were adding an acid, so it reacted with the base part of the buffer. And the bottom one, we added sodium hydroxide, which is a base, so it reacted with the acid part of the buffer. Question? What's that? Yeah, that means we didn't make any free OH minus in this reaction. Like free by itself, like you don't see, there's no OH minus on the product side, yeah? None of that over here. And that's very different than what happened when we added it to water. We made nothing but OH minus, right? And is those two things, the free OH minus or the free H plus that affects the pH, not attached to anything. So just freely floating around H plus and OH minus in the solution is what affects the pH. And the way a buffer functions, because it does have an acid part or a base part, when you add additional acid to it, it's able to handle that H plus coming in and not allow it to be free. And when you add additional base to it, it's able to handle that OH minus and not allow it to be end up being freely floating in the solution. And both of that, basically by tying up those two things, it prevents big jumps in the pH because the H plus concentration ultimately remains relatively constant. What's that? It does. So for example, in this situation, when the OH comes in, it actually will grab the H off of the acid and it will make water, right? And that F minus will then just be floating around freely. Again, it kind of ties it up in the case of this one in water. Up here, the H plus coming in gets tied up with the F minus and gets tied up now as HF. So it kind of ties it up and doesn't allow it to be freely floating in the solution. And that's ultimately what keeps the pH from going crazy. Other questions? So that is really important that both of those things are in there to begin with for a buffer to work correctly. Now, let's just say, for example, you can think of it like this, that, you have a buffer basically, and the buffer itself has an acid part and it has the base part basically to it. So what happens is, again, as we just saw there, when you add additional acid, it will react with the base part and use some of it up, but it will generate some of the acid part. So dramatically drawn here, we will see a big jump perhaps in the acid part of the buffer, but we will see a decrease in the base part of the buffer. And same thing here, if you add base to this, additional base, it will react with the acid part and it will generate more of the base part of the buffer. And it will use up, like I said, some of the acid part of the buffer. Now, there is a limit to how effective a buffer can be. It is sometimes referred to as buffer capacity. And when you make a buffer in real life, you do want to make it so that it can function correctly. And what I mean by that is, when you make your buffer, there's only a certain amount of moles, for example, of the acid part of your buffer and the base part of your buffer there to react basically with whatever's coming in. And it's really important when you make your buffer that you make it the correct molarity to handle whatever you're going to add in terms of acid or base to it. Otherwise, you can essentially blow through a buffer. Now, let's just say, for example, I continuously add acid to this buffer. What's going to keep happening as I continuously add acid? Every time I add acid, what part of the buffer gets used up? Base part. So every time I add acid, I just keep adding. I'm just going to keep chewing, right, away at my base part of the buffer until at some point there is no more base part. And if you continuously add acid at that point, you are then just adding a lot of H plus really quickly. And you would at that point see a pretty big drop in the pH because you basically just blew through your buffer, right? Or let's just say you grabbed, instead of the 0.1 molar sodium hydroxide, you grab the 18 molar. Seems close. And you add that to your buffer, right? Your little buffer here probably doesn't have enough acid part to handle all that base coming in, and you're going to blow right through it. And once again, as you continue to add the base, you will eventually blow through the acid part and just start adding OH minus, and you will then see a really big rise in the pH at that point. So you can blow through your buffer if what you're adding is too strong, if you will, for the buffer you made, or if you just keep adding it. Where's a real life example of you just keep adding it? And you did this when you do a titration. Yeah, when you did titration with vinegar and sodium hydroxide, you keep adding base, and at some point you blow through a buffer and you see a really big jump in the pH. And that is one of the reasons, perhaps, as we'll talk about in this chapter, the famous saying that people say, which is, I just added 1 drop and my phenolphthalein went like super dark pink. I don't understand it, right? It was colorless a second ago, and then it went super dark pink. And then your bad instructor told you to do it again. It's too pink. Hopefully not. But we'll talk why that happens, by the way, shortly. So this is really important. There is buffer capacity. You can blow through a buffer if you do that. Now, how do I know how I should make my buffer or what I should make my buffer out of? You could actually use the Henderson-Hasselbalch equation, which, by the way, is really the equation that is used in a buffer situation. So this is really the equation. I know we talked about common ion, but for the most part, you're going to see it as a buffer situation because a buffer is a common ion situation that's occurring. Now, if you use your Henderson-Hasselbalch equation here, and you make a buffer kind of like what I did right about here, equal concentration of your acid part and your base part, and I put that into my Henderson-Hasselbalch equation, that will essentially give me the log of 1, right? Log of 1 is equal to 0, yeah? That means that the pH equals the pKa. So if you're looking to make a buffer at a specific pH, you should find a acid or base that has a pKa value of plus or minus 1 of your desired pH for your buffer. So if you wanted to make a buffer at a pH of 9.4, you should not grab acetic acid because it has a pKa value of like 4.74, which is way, way, way too far away. You should grab something like ammonia, which has a pKa value of 9.25, which is very, very close to what you want. So if you have to choose, like, what should I make my buffer out of, that is really your goal. Closest pKa value to your desired pH is best because it doesn't require as much kind of manipulation of reagents, but you're looking for plus or minus 1 pKa value of your desired pH of the buffer that you're making. Any questions on that? Yeah. If you added too much of a buffer, it wouldn't if it's the buffer solution. So it depends what you're adding it to. If you're talking about taking a buffer solution and just dumping it into another solution, it depends. If it's like an acid or base, it would start reacting, obviously. So it could eventually change pH depending on what you dumped it into. But if you just made a big old vat buffer, basically, it all should ideally be the same pH when you dump it into any beaker you want. And then obviously whatever you add to it would change it depending on what you add and stuff like that. By the way, that's why you could really, with a buffer, dial in the pH of your buffer that you make, because if you go and measure out everything and do the calculation to measure out how to put all these together, obviously you could go find your acid, your weak acid, you can find your conjugate base, and you put them together. You most likely will not measure out exactly the right amount, nor will maybe the pH of the water and all that be perfect, ideal. So typically when you go to make a buffer and you put your pH meter in there to check it, it's probably not very close, or it is close, but it's probably not exactly to the pH that you calculated. And because a buffer can resist changes in pH, you could actually dial in your pH of your buffer to the exact number you need by literally just putting in drops of like acid or base to either raise or lower the pH, and you can literally dial it into exactly the pH that you need. And again, because it will not jump really big in pH, you could add slowly acid or base to it to get it to exactly the pH that you need when you start. And that's usually what you have to do when you make a buffer. It's usually never like right on the number that you're looking for. All right, now that we know about buffers and how they work, again, a reminder that a buffer solution will be able to resist that change in pH, while something like water, which is not a buffer, will not. So take a moment here for each of them, decide, can these be a buffer system or not? Okay, so looking at the first one here, we got KF and HF. And once again, this is a salt, and that means that this is K plus and F minus, so that is F minus and HF. So that is the one we were just looking at, and that definitely can be a buffer as they're related to each other. HF is a weak acid, so that is good, and that would be the salt of its conjugate base. Taking a look at B, that is KBr and HBr. So again, this is a salt, K plus and Br minus, and HBr. These are the two guys related to each other. Can that be a buffer? The answer is no. Why is that not a buffer? What type of acid is that? Strong, yeah. So remember, a buffer cannot be made up of a strong acid or a strong base. This acid would not be able to set up that equilibrium that's needed to keep, again, that buffer components in the solution. So this is not. And then here, this is a little sodium carbonate, a little sodium bicarb. And they're both really salty here things. So we'll go CO3 2 minus really, and HCO3 minus. These two guys are the thing that are related to each other by 1HF. Our 1H plus, and obviously sodium is just hanging out there. This is going to be a buffer, right? As that comes from carbonic acid, which is a weak acid. By the way, I know that because carbonic acid is not one of the 6 strong acids, right? So process of elimination there tells me this is going to be a weak acid, and that would be its conjugate base in this case, would be carbonate. Any questions on any of those there? So again, for something to be a buffer, need the basic Bronsted-Lowry definition of 1H plus difference between the two. And the second thing, you need it to be weak, either acid or base needs to be there. All right, so let's talk a little bit about some calculations here. So why don't you start with A, calculate the pH of a buffer system that contains 1 molar acetic acid and 1 molar sodium acetate. Here's the Ka value of acetic acid. So see what you come up with here. Okay, let's take a look at the first one. They were nice enough to tell it's a buffer, so that makes the calculation pretty easy. So in A here, we got 1 molar acetic acid, which is a weak acid with a Ka value of 1.8 times 10 to minus 5. And we're going to have 1 molar of sodium acetate, which is a salt. Once again, this salt is sodium ion and acetate ion. So our buffer really is these two things here, right? Is our buffer in this case. And that again is our acid part of our buffer. And obviously this is our base part of our buffer. So because I know it's a buffer, I can just go right into the Henderson-Hasselbalch equation. You could also do an ice table if you wanted to. So that is not it. Let's try it again. pH is equal to the pKa plus the log of the base over the acid. That's going to give us a pKa here of negative log of 1.8 times 10 to the minus 5. That should be a 4.74. So that'll give us pH is equal to 4.74 plus the log of 1 over 1. Once again, that is going to equal 0. And that's going to give us, basically for part A, a pH of 4.74 in this case. First off, any questions on that? Once again, if you want to not use the Henderson-Hasselbalch equation, probably the best bet would be to set up your equilibrium here with your acetic acid. And again, you could take an ice table approach if you wanted to. The important part there is right here. Again, you need the 1 on both sides in this case. The rest of it would be just like normal here. And obviously into your Ka, and you'll eventually get to your 4.74 when you solve for X and get the H plus concentration. Any questions on A? Yeah. It may not. So a lot of times, sometimes the problems will not say that it is a buffer. So again, being able to recognize that they are related to each other, those are the things you want to kind of think about. Is this a buffer or not? Sometimes they will, but a number of times they really won't. They'll just kind of go, hey, you made a solution out of these two things, and they assume that you kind of know those two things. Well, when they come together, we'll make a buffer. Other questions? All right, so let's take a look at B. What will be the pH of the buffer system after we add 0.1 molar HCl? In this particular problem, we're going to assume that everybody's volume just stays at 1 liter just to make the math a little bit easier. That is not always the case, so you do have to take into account the volume in most cases. But for this first one here, we're just going to assume everybody just stays at 1 liter. Everybody's 1 liter in terms of their volume. Now, one of the important things to think about is molarity. And molarity, when we add volumes together, does the molarity stay the same or does it change as you add one volume to the next? Molarity does change as you add volume to the next. And that's really because molarity is moles of solute, right? Liters of solution. So when you mix solutions together and volumes together, that bottom part keeps changing, which means the molarity keeps changing as you do it. The one thing that actually stays the same is the top part there, which is the moles of the solute. So the moles stay the same, but the molarity changes. So it's really important whenever you come across a problem, and one of the problems where you come across this is right here. You have a buffer, and then you want to add some more acid or base to it, so you're adding volume to volume. You need to do the calculations in moles and not molarity. And the second place this happens a lot is what we'll talk about next, which is titrations, right? Think about titration. You're doing nothing but adding volume consistently all the way through to titration. So the molarity is constantly changing, but the moles will remain the same. So by the way, when you have something with a molarity, it's the moles is actually the thing that's reacting, right? The moles of the solute that's in the solution is really what's floating around there and really what has the ability to react. So how do we do this? We do need to do an ice table, and the purpose of the ice table is to see, in this case, how the buffer is changed by whatever you added, the acid or base to it. So the rule is if you need to do an ice table in moles, you should do the ice table in moles. But as soon as you're done with the very first ice table that you did in moles, you then should convert it back to molarity at the end, everybody, by using the total volume. And that's because probably in most cases, if you're going to take those numbers and maybe continue on with them to do some other calculation, you'll need molarity in most cases. And that's just a good practice. Moles on the first table, automatically when you're done, just convert everybody back to molarity by using the total volume. And then you'll usually be in the right unit that you need if you need to continue on and do further calculations with those numbers. So let's take a look at this together and sort of see how we would do this. And again, in this situation, we're going to assume everybody has 1 liter of volume. It's going to be constant. It is normally not constant, so you normally have to kind of take the volume into account. We had our same molarity of acetic acid in a solution with our same molarity of sodium acetate. Same Ka value, 1.8 times 10 to the minus 5. But in this case, we're going to add 0.1 molar HCl. So in this particular case, we do get a reaction that's going to happen. So when I add my HCl to my buffer here, it's going to react with the base part of my buffer. So we'll get this reaction that's going to occur. And by the way, one of the nice things that we do know is in this reaction, we should also make the other part of the buffer. So we kind of know what the answer is over here. This is going to do a double displacement reaction where these guys are going to switch partners. And that's going to get me here some acetic acid and some sodium chloride in this particular case. I think I'm going to erase my lines there. So when we add this acid to this buffer, it does require an ice table. And once again, the purpose of the ice table really is to see how our buffer is going to change as a result of adding that. So initially here, we do need to do it in moles for everybody because we added, right? So in this case, it's very simple to convert to moles since everybody's going to be 1 liter times 0.1 moles per liter, 0.1 moles here. So this would be 0.1 moles of HCl. Same thing for our molarity here. 1 times 1 is 1, so 1 mole of our acetate. And again, a super common error right about here. We also have that as well. So that's going to be 1 mole of our acetic acid. If I don't put that guy on the right, I am not doing the buffer problem, right? So again, it's really important to make sure you have that guy on the right. It is very commonly missed a lot of times when people do these. So what's going to happen here when I add my HCl to this buffer? If my buffer is made correctly, my HCl should still be there or go away. It should go away, right? That's the purpose of the buffer, to handle any HCl that's coming in here. So when we do an ice table here with moles, we're actually not going to use X's because we actually know what the change should be. And the change should be what we're adding in this case, which is our HCl. So the change actually should be 0.1 moles. By the way, it should always be the smallest number when you do this because if you take the larger number, you get a negative number, and that should not happen. That would be minus 0.1 moles. We will have plus 0.1 moles on this side. And at equilibrium, what that's going to get us here is obviously 0. And then we would have 1 minus 0.1, which would give us 0.9 moles. And we'll have 1.1 moles over here. First off, any questions on the ice table? Yeah. That was my next question. Why did I ignore the sodium chloride? Because it's neutral. Yeah. So we already know the sodium chloride is neutral, right? So no need putting numbers that you shouldn't be using anyway. So might as well just leave it alone and not touch it. It will have no effect on the pH. And that's really why I didn't put any numbers there. Yeah. Other questions? All right. So at this point, it's really important, like I said before, it's just really good practice to definitely convert everybody back to molarity at this point. So do the table of moles, convert back to molarity. In this case, our total volume, since we're keeping it constant, is going to be 1 liter. In a case where we don't keep it constant, you need to add, obviously, the volume of the buffer and the volume of the acid you added, right? That would get you your total volume is what you would get there. In this case, we would divide by 1 liter. And that's going to get us 0.9 molar and 1.1 molar here. Now, if you were lost maybe of like, what should I do next? You should always look at your ice table. It does give you some important information. One of the important information it should give you is when we reach equilibrium, I have that guy left and I have that guy left. You hopefully should still recognize both of these things as being a buffer. Yeah. And what that allows you now is because you know you have a buffer left over, you can go right into the Henderson-Hasselbalch equation and get the pH of the solution. Or if you prefer, you can still do another ice table. So again, it's up to you. If you don't want to do the Henderson-Hasselbalch, you could still do another ice table. The pH here will equal our pKa plus the log of the base over the acid. Same pKa value, 4.74, plus the log of the base, which would be this guy here, 0.9, divided by our acid, which would be that guy. And what we're going to see here is a pH of 4.65. Again, you could do a nice table with acetic acid. Just again, you need the initial concentrations on both sides, right? So that's important. Question on that. Did my buffer work? Well, I started with 4.74 and then I added a little bit of acid and it went down a little bit. And that's also a good thing to think about because I added acid, it should go down a little, right? So if I did this calculation and I ended up with a pH of 4.9, I'm going in the wrong direction based on what I'm adding, right? I'm adding acid, so I definitely going in the wrong direction. Could happen perhaps if you flip the base and acid by accident in your equation. Any questions on that there? So if you add any acid or base to a buffer, it does require one ice table. It does need to be done in moles to begin with, converted back to molarity at the end. Then you could go into the Henderson-Hausbach. Again, the purpose of the ice table is to figure out how your buffer changed as a result of adding either the acid or the base to it. All right, so why don't you try one here? Calculate the pH of a 0.3 molar ammonia, 0.36 molar ammonium chloride buffer system. What is the pH after the addition of 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of the buffer? So we're looking for two answers. We're looking for the pH before you add the sodium hydroxide. Then we're looking for the pH after you add the sodium hydroxide. I'll give you a Ka value here. I'll do Ka. We could do Kb too, by the way, but we'll do Ka. 5.6 times 10 to the minus 10. That's the Ka value for NH4 plus. Or if you prefer, the Kb value for NH3, 1.8 times 10 to the minus 5. Okay, let's take a look, see how you're doing. So we're looking for two pHs, the pH of the buffer beforehand. By the way, I do know this is a buffer because these guys are related to each other by a difference of 1 H plus, because that is a salt of NH4 plus and Cl minus. So once again, our buffer components are really these guys right here. So since it's a buffer, before I do anything to it, I could go right into the Henderson-Hausbach equation. I don't have to worry about moles or anything like that. I could use molarity because we haven't added volume. So for part A here, before, we could go right on into that there. And since I do have an option here, KB or KA, as I did put the KA here, I'm just going to use that to get the pKa value here, which will be minus the log of 5.6 times 10 to the minus 10. And that's going to give us a pKa value here of 9.25. You could have used KW, get the Ka value if you were given the Kb or could only find the Kb. You could also calculate the pKb and then subtract 14 to get the pKa, so you could have done that. Alternatively, you could also have used the POH version of the Henderson-Hausbach equation with the Kb value and the pKb. That's an option as well. So there's a few different ways you could actually go about doing this. I'm going to go with the regular old Henderson-Hausbach here with our pKa value there of 9.25. Plus the log of my base. So NH3 is my base over my acid, which is the NH4 plus. Once again, NH4 plus has one more hydrogen than NH3, so it is the acid, and NH3 is a weak base, so I should know that as well from my Kb value here, or this guy's Ka value, whichever one you want to look at. That's going to give us an opening sort of pH for our buffer here of 9.17 in this case. First off, any questions on part A here? All right, now part B, we're actually going to add some sodium hydroxide in this case. to our buffer. So we're going to add 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of my buffer. So essentially I have a little beaker over here with my buffer in it, a little NH4 plus, a little NH3, and it is 80 milliliters. And to that, I'm going to add my 20 milliliters of sodium hydroxide basically to it. So because we're adding volume, obviously here we do need moles of everything. So I'm going to calculate the moles of everything here before I begin. I do need to convert that to liters. So 0.02 liters times the molarity of my sodium hydroxide, which would be moles per liter here. And that's going to get us 0.02 times 0.05 will give us 0.001 moles of sodium hydroxide. We'll also convert our buffer components into moles. The buffer is made up of both of those things together in the same beaker, which means the 80 milliliters goes for both parts of the buffer. So 0.08 liters times the molarity of my NH3, which is 0.3 moles per liter. And that's going to get us here 0.08 times 0.3, 0.024 moles of NH3. We'll do a similar calculation here for our NH4 plus, also 80 milliliters. Converted to liters times 0.36 moles per liter of our NH4 plus, 0.08 times 0.36, 0.0288 moles of NH4 plus. So we got our moles of everybody. Now we are ready to do our actual ice table that does need to be in moles. So when I add that sodium hydroxide to my buffer, it is going to react with the acid part of my buffer, which in this case is the NH4Cl, right? It is going to do a double displacement reaction, and you're actually going to get a few things as a result of this. You are going to get some sodium chloride. You are going to get some water. And you will actually get some NH3 at that point here. So you actually get three things happening. The sodium and the chloride come together. This guy's going to donate an H plus over to the OH to make the water, leaving an NH3 that's left over when it does that, yeah, at that point. All right, so now that we got all that, let's do our table here. I'll get rid of that line here. So initially, we have 0.001 moles. For our NH4 plus, we got 0.0288 moles. I'm not going to worry about the sodium chloride because it's neutral. I'm not going to worry about the water because it's neutral, right? So I'm just going to kind of ignore those guys. And that's going to give me my 0.024 moles of my NH3. Once again, if you forget the guy on the right, you did not do a buffer problem, right? The change here should be what we're adding. And remember, always it's the smallest number. Even if your head tells you it's not the smallest number, it is the smallest number. That's the one to choose. So we're going to go minus 0.001 all the way across, and then obviously plus on this side here. That's going to get us, when we reach equilibrium, 0 of our sodium hydroxide, 0.0288 minus 0.0, we got there 2 zeros, right? 0.1. 0.0278 moles. And we're going to add on this side 0.0025 moles. Once again, as I mentioned before, it is good to convert this back to molarity at this point, even though really moles would work in the Henderson-Ausbach. But here our total volume is, we had 80 mils of our buffer plus 20 mils of the base. That is a total volume of 100 milliliters. So we're going to divide each of these by 0.1 liters, which is 100 milliliters converted into liters. So we get molarity. And we're going to end up with, at this point, 0.0278 divided by 0.1. Got to move the decimal place there. 0.278 molar and I feel like I put an extra zero there. I felt just combine those to one big zero at that point. There you go. I think that's a little bit better if I'm not mistaken. 0.25 molar. Yeah, so that should be a zero there. All right, so at this point, once again, if you are not sure what you got going on, you could look at your ice table. I have this guy left over. I have this guy left over. These two guys, once again, are still a buffer at this point. So you do have, again, two options. You could Henderson Hasselbalch it, or you can ice table it. I'm going to Henderson Hasselbalch go here. I think you could probably see it here. The pH would equal our pKa, which is the same from above, 9.25, plus the log of our base, which is over here, 0.25 divided by 0.278. And let's see how we did here, maybe. We end up with a pH, I'll go right here and just circle it, 9.20 in this case, yeah. And again, you could ice table it at this point. And really with the ice table, you still actually, in this case, actually have two options as to how you can do it. You could either do like a Ka table where you would start with the NH4 plus, or you could do actually a Kb table if you prefer and do it with the NH3. Again, if you do the Kb table, you get hydroxide rather than H plus. So again, you got to watch out for that if you kind of go that route. Our buffer here did its buffer thing, right? We started with a pH of 9.17. We added some base to it. It went up a little bit to 9.2, which is good, and moved in the correct direction based on what we added. Any questions on that there? All right, we will lay it up there.